So the tests are coming back tomorrow, maybe late tonight if I can stay up late. There's marked anyway. Any other questions? It's getting to be more complicated stuff, isn't it? It's not, I don't know, so much harder, but it's complicated, right? We want to do some more triple integrals tonight and recognize that we have a lot of trouble with those things because by the time you take an integral of an integral of an integral, somewhere along the way you get something you can't integrate. Triple integrals can sometimes be simplified by a change of coordinates to something that takes into account the symmetry of the integrand or the symmetry of the solid you're integrating over. So we're going to do triple integrals in cylindrical and spherical coordinates with the idea that there's lots of solids and functions to integrate that become easier in these coordinates. Lots of things with a radial symmetry of some sort out there. And you recall these coordinates look like this. Cylindrical coordinates are really just polar coordinates add z, right? Except that r couldn't be negative. And the reason r can't be negative is it becomes inconvenient trying to do triple integrals. R can switch signs that leads to problems in the theorems and so forth. So there's no loss of being able to describe the points, just keeping r non-negative, and we do that for cylindrical coordinates. So if it's just polar coordinates with r non-negative, then instead of saying like you did in polar coordinates, r squared equals x squared plus y squared, remember that? And r can be positive or negative. We'll say r is the square root x squared plus y squared for cylindrical coordinates. It's non-negative. And then theta has to go into the same quadrant as the point is y over x. So tangent theta is y over x, quadrant of xy is its terminal ray. That converts the polar coordinates and then just z equals z for the third coordinate. And in some sense, we've already done these because we did triple integrals where we had to reduce the polar coordinates and it effectively amounted to this. And the other way you can say x equals r cosine theta, y equals r sine theta, just like polar coordinates, and c equals z converts the other way. So those were cylindrical coordinates. You converted between those two. One of the reasons they're called cylindrical coordinates is that things have with a cylindrical symmetry have an easy equation, right? For instance, if you put the equation r, the radial coordinate, equals some fixed number r, what do you get in the xy plane? You get a circle of radius r, right? It's all points at a distance r from the origin, capital R from the origin. And then since z is arbitrary.
Excuse me, Professor.
Yeah.
Can you tell me what is a classroom?
Oh, it's in MCS 109 now. I sent an email, but maybe it didn't get to everybody or wasn't clear. Yeah, MCS 109.
109? Okay.
Yes.
Thank you.
All right, so if the equation of the surface is r equals a constant r, then this goes up and down forever. Then what you get is a cylinder, hence the name cylindrical coordinates. If you put z equals a constant, then you get a horizontal plane. And if you get theta equals a constant, you get now a half plane. In polar coordinates, you get a line, but here, since r is not negative, you get a half plane with the angle here, theta equals theta 0. And then arbitrary, you can go arbitrarily far out, and then z arbitrary, you go up and down, you get this half plane. So anything with those kinds of descriptions, like a solid that's bounded by half planes at the origin, like if you get a wedge of cheese, this is perfect for cylindrical coordinates, right? Something like a wedge of cheese where it's bounded between two half planes at the origin and then a cylinder out here, right? Then you've got constant bounds, right? R goes between 0 and this radius, and theta goes between this angle and this angle. Constant coordinates for your integration. So these are easy. So we're called cylindrical coordinates, and then these shapes make easy integration limits. Half planes coming out of the z-axis, horizontal planes, and cylinders. Such as this wedge of cheese. Here it gets half planes and the circle on this side. So there's an example. All right, now then we also had, and then I need to draw the coordinates. See, the way that came out was you took any point here. If you dropped a perpendicular to the XY plane, then you call that the Z coordinate, just like in rectangular coordinates. But then this radial distance back to the origin was R. And you take that line segment to the origin and take the angle on the XY plane over here, and you call that theta. Then these are the cylindrical coordinates, R, theta, Z. You always put them in that order. So hopefully that looks familiar, right? Okay. And then spherical coordinates. It's going to be on here, I think. Just to remind you. These have their name because an easy, if you put rho equals a constant, these you get a sphere. But if you take arbitrary point up here, you can give it coordinates rho, theta, and phi, where rho is the radial distance from the origin. Theta is the same thing you have in cylindrical coordinates. So as you drop a perpendicular XY plane, I won't draw this solid this time because it's not giving a coordinate. But then this line over here, the angle on the XY plane is still called theta. And then the third coordinate is phi, the angle down from the z-axis. So there's rho, theta, and phi for spherical coordinates. And these had the following equations. We better move this over just in case. Rho is now the distance from the origin, so it's square root of x squared plus y squared plus z squared. That's just the distance formula, right? It's the distance from x minus 0 squared, y minus 0 squared, z minus z squared square root is the distance formula for the distance from 0, 0, 0 to x, y, z. Right? That's the distance formula from 0, 0, 0 to x, y, z. And then theta is the same as before, so you still put tangent theta equals y over x. With theta in the correct quadrant. Remember, there's two thetas that will have this ratio. One will point into the same quadrant, one will point directly opposite to it. So theta has to be the quadrant in the xy plane of the point xy, just like over here in the xy plane. And then phi, if you look at this diagram, drop a perpendicular back to the z-axis. You notice that the cosine of phi, here's phi, is this, which is the z coordinate, the adjacent side to phi, over the hypotenuse rho. So cosine phi equals z over rho is the way they often put this. That'll convert x, y, z coordinates to rho, theta, phi, where here you replace rho with the square root and just have all x, y, and z on this side if you want. So there's the conversion from x, y, z to spherical. And then the conversion the other way with x equals rho, cosine theta, sine phi, y equals rho, sine theta, sine phi. I won't go through all the derivations unless you ask me. And c equals rho cosine phi, we already did. And divide that by rho, you get this equation. This is the way they usually print it in textbooks because you figure z over rho and figure what angle has that cosine. equivalently, you can write this as phi equals the arc cosine of phi over rho. This actually always works because the arc cosine gives the unique angle between 0 and pi that has that cosine, and that's what you want. You only let phi go from 0 to pi. You don't let it go on forever like you do theta. Theta can be any angle between plus and minus infinity. But phi is only allowed to go from 0 to pi because, again, if you go further than that, then it wraps back around to the opposite angle theta, and there's lots of problems with integration that we're going to develop here. So those are the transformations for those coordinate systems. Any comments or questions on those? Does it look familiar? Then similarly here, some easy integration coordinates come for a sphere, right? Because what's the equation of a sphere of radius r? So this is a radius r sphere. Well, the equation is just rho equals r, right? It's all points at a distance, if the sphere is at the origin. All points at a distance from the origin r is a sphere at the origin. The other thing you can get, suppose you put phi equal a constant, what kind of figures do you get if I put phi equal a constant? Now I come down a fixed angle phi equals some number phi 0. Well, I can let theta be arbitrary, so I can rotate all the way around. And then I can go out an arbitrary distance with rho, right? And so I get this half cone. So a sphere has rho equal constant. A half cone is what you get when you put phi equal a constant. Although if you put phi equal pi over 2, you actually get the xy plane. And if you put phi equals 0, you just get the positive z-axis. Phi equals pi gives just the negative z-axis. So you get those special cases. Those aren't as much interest. But phi equals phi 0, other than those three cases, is a half cone. And then if you put theta equal a constant, once again, just like in cylindrical coordinates, it's the same theta, so you get a half plane at the angle theta. So these are good for solids that are bounded by half planes with the edge on the z-axis, half cones with the vertex at the origin, or a sphere at the origin. Those things have easy constant limits in spherical coordinates. But keep that in mind when you look at the homework problems and so forth. Hope that wasn't too much review, but I think the examples of constants is kind of important there and see why they're the case. All right, now what we want to do is talk about integration. You can probably guess this one. Integration of cylindrical coordinates looks like this. Suppose I have a solid that's generated like this. It goes between some angle theta equals alpha and some other angle in the xy plane, theta equals beta. And it doesn't look like an arc of a circle necessarily. Let's say it's like that or something. R equals R2 of theta on the outside and R equals R1 of theta on the inside. What does that look like, or what is that called in the plane? What we call that? It's just this book's term. If we take this region down here, we call that a simple polar region if R was continuous. Both these functions were continuous. Now, suppose we have a solid that sits over such a region. Suppose this is the region of projection, and we have a solid over that that's bounded on bottom by some surface, z equals z1 of r and theta on the bottom. There's your bottom surface. And it's bounded on top by some top surface over that. We have a the solid like this, and on top, this one is Z equals Z2 of R and theta. How could I integrate over a solid like this? And maybe I'll switch to the book's terminology too. I've been calling it T because I forgot what the book calls it. They call it G in the book. Suppose the solid is called G. How do I integrate over G in cylindrical coordinates if maybe I have some nice symmetry like that I want to take advantage of? What I can do is kind of like I did in rectangular coordinates. Remember in rectangular coordinates, what do? We surrounded our solid with a big rectangular box, right? And then we partitioned that box in X, Y, and Z, took all the subsolids and added up over all the subsolids. We'll do the same thing here, where we partition over a region like this that encloses, oops, it needs to go taller, that encloses a solid G going between constant endpoints. And we take this big region like this and we partition it in theta. We partition it in Z. And we partition it in R. And so we break it up into a whole bunch of subsolids like that. Subsolids are now this kind of a region. This will remind you a lot of polar coordinates because it's just polar coordinates at Z. Each subsolid is like this. And it has an angle change, delta theta k for the k subsolid. We partition it into n subsolids and take the limit of the sum again. That's what we're going to do. So delta theta k is the change in angle. And then delta rk is the change in radius. And delta zk is the change in height. Well, what is vk, the volume of this subsolid? What we want to do is add up all these volumes and then multiply each times the function at that point. Call that the triple integral of the function over this. Well, delta theta k is actually the angle there, and if you want to find the volume, what you can do, this goes back to the origin here, by the way. This is a sector. This is your radius rk minus 1. This is your radius rk, and delta rk is rk, the kth radius minus the k minus 1 radius. And what you have is the area of the base needs to be multiplied by the area, by the height, delta zk, right? So base area times height gives you the volume. But what's the base area? It's well, it's a piece of a sector, right? Here's rk minus 1, and here's rk, and the base, that looks like this. And you know the area of the big sector is 1/2 r squared times theta, the angle that you turn through. Call it delta theta k. This is just from the geometry, right? If you have a sector and its radius r and angle phi, what you say is the area formula for that is 1/2 r squared phi, right? Remember that formula? That's what I'm using here, 1/2 r squared phi, except the radius is rk, is little rk, and the angle is delta theta k. So I'm just using this area formula for a sector. A slice of pizza, right? Radius, constant radius, a piece of a circle out here, and then straight lines there. And then that's the area of the big sector here. Then I subtract off the area of the little sector here, so it's minus 1/2 rk minus 1 squared delta theta k. and then all times delta zk. And if you break this out, you can factor out a 1/2 delta theta k times rk squared minus rk minus 1 squared. All right. And then this one factors as 1/2 delta theta k rk plus rk minus 1 times rk minus rk minus 1, right? That's the volume of the kth subsolid. Now we can call this this. This is 1/2 rk star delta rk delta theta k. Because rk minus 1, rk minus rk minus 1 was defined to be the increment in r. It's delta rk, right? So that's that part. These deltas are always confusing, but delta rk is one variable. K for the kth subsolid and delta r for the change in r. So the rk star, if I define rk star to be the rest of this, I let rk star be the average radius. It's rk plus rk minus 1 all over 2. This times this, and this give the other two parts, right? The delta theta k and the delta rk. So those are the same just by making these definitions. Now, finally, this is pretty fast.
What happened to the Z?
The B?
The Z.
Oh, the V. Oh, I'm saying VK is the volume of the kth piece. And it's the base area times delta ZK, right? The base times the height. The base area times the height is the volume.
Where's the height going though?
Oh, I forgot the delta Z you're saying. Yeah, you're right. I forgot. Yeah, thank you. I had to come back and get that. Delta ZK. Yeah, all this is multiplied by delta ZK. Sorry about that. Move the forward bonus only. Yeah, I'm gonna need that in just a second. Delta ZK on each one of these. Just on the end. Appreciate that. All right, now what is that? The triple integral of a function f of x, y, z is going to be the sum over all those subsolids of the kth piece. We'll have this notation. Integral over the solid G is going to be the limit as the number of solids goes to infinity. Let's call it capital N, I guess it doesn't matter. Number of subsolids of the sum k equals 1 to n, f of any intermediate point xk star, yk star, zk star in the kth subsolid times delta vk, just like we do with rectangular coordinates, right? Same thing. But now we're going to do the volumes this way with cylindrical coordinates. So this is going to be the limit as the number of subsolids goes to infinity of sum k equals 1 to n, and f of any intermediate point xk star, yk star, zk star, and delta vk is this. That's I didn't do this right. RK star includes the 2, so the half is out here. RK star is this times a half. So it's just this is what we have. we define RK star to be the average radius halfway between the two radii, right? Then this and this becomes RK star, this becomes this, and this becomes this by its definition. All right, and then delta ZK hangs on. And so now this is RK star, delta RK, delta theta K, delta ZK. And, well, these are rectangular coordinates. If we convert them to cylindrical coordinates, this is the limit, n goes to infinity, sum k equals 1 to n. We can pick any points in here we want, provided this function is continuous, and this limit of the sum will be the same. Our xk star could be rk star times cosine theta k star, any angle in the increment. Yk star could be rk star, the average radius, times the sine of any angle in the increment, theta k star. And zk star just remains zk star, any z in the kth increment. And then times rk star, delta rk, delta theta k, delta zk. And now the question is, what is that? We already defined what that is. By definition, this is the triple integral of this function of r, theta, and z, right here. This is the integrand, and this becomes the dr, d theta, dz in the notation. The notation for this as a triple integral is the integral over the solid of f, and you just place the k stars with the variable, f of r cosine theta, r sine theta, z, rk star becomes r, this becomes dr, d theta, dz, just by definition of the triple integral. Except there's something clever going on here. This is with respect to the new variables. It's looks like rectangular subsolids if you drew r, theta, and z rectangular, but it's still the same definition. By definition, this is this thing. And so the book will sometimes put this. They'll call this dv r theta z, something like that. They'll say this is the little volume, infinitesimal volume element, and they'll give it that notation in order to not have to write this out. But there is the evaluation of the triple integral in cylindrical coordinates of a function f of x, y, z. You can evaluate it in cylindrical coordinates like this, and now if you do that, maybe you can get constant endpoints if it's something nice like integrating over a wedge of cheese. Right? And there is one little thing I left out here. Really, to be completely detailed on this, you don't put f in here, you put this f hat. Remember what f hat was? F hat was equal to f if you were in the actual subsolid. F is only defined over this green subsolid. It's not necessarily defined in this enclosing solid here, right? It's bigger. So this has to be a closed bounded region again in order to be able to put it inside a bigger solid and partition it up. But for a closed bounded solid, we put it in the big solid, and f is not necessarily defined outside of the original solid. So f hat is equal to f if you're in the original solid, and it's equal to 0 if you're outside. Then this adds up appropriately. So we need to make this note. F hat of x, y, z is equal to f of x, y, z for any x, y, z in the original solid, but it's equal to 0 for x, y, z not an element of the original solid. This symbol means element of. So with that definition, then this is the triple integral. Now we can do these interesting kinds of things. And here's the first kind of example you want to be able to do for the homework. It's not uncommon to come up with this kind of triple integral in rectangular coordinates and have trouble with it until you convert it to cylindrical coordinates. Suppose I had to evaluate this following triple integral. Minus 1 to 1, 0 to square root 1 minus x squared, 0 to square root 1 minus x squared minus y squared, e to the minus square root x squared plus y squared plus z squared, dz, dy, dx. What a mess. Can you imagine trying to evaluate that in rectangular coordinates? I mean, you integrate this. How do you integrate this in the first place? It's not an elementary integral. But if you could do that, now you got to plug in this endpoint. And you can see the integration just becomes undoable. But you notice something really nice about this. What does this look like in cylindrical coordinates? And this is the hint. When you see the square root 1 minus x squared, square root 1 minus x squared minus y squared, that's a hint that this actually works better in cylindrical coordinates. What you do to convert it is first sketch the region and then convert it to cylindrical coordinates. Sketch the region G, I guess I should say the solid G. Region, they usually mean a plane region. What does it look like? This is a simple polar region on the outside, a type 1 region on the outside, and then a top surface and a bottom surface, right? So this is the top surface in x, y, z coordinates. Z equals this, and z equals this is the bottom surface, right? Thinking of our projection theorem. And then this is the integration over the plane region. This is the projection region R for the last time. And so this is a terrible integral, but if we sketch it in cylindrical coordinates, it's not so bad. What we want to do is first sketch the plane region R. We can say, well, it's a type 1, right? Because x goes between the constant limits. So x goes from minus 1 to 1. Then the bottom curve is y equals 0. I should have put that on here. Bottom curve for the plane. And then here's the top plane curve. So the bottom curve is y equals 0, and the top curve is y equals square root 1 minus x squared. Well, I'm going to say actually it's a half circle. Why do I know that? I square both sides, right? And it becomes y squared equals 1 minus x squared. Then I add x squared over, and I have x squared plus y squared equals 1. Oh, it's just a unit circle. So what I want to do is now the square root means that y is non-negative, so it's the top half of the unit circle, right? So the top half of the unit circle is this one, and the bottom is the line segment y equals 0. And this is our region R of projection. Now, what lies over that region, here's the region of projection drawn in 3 space, goes from minus 1 on the x-axis to 1. That's the same R. What's the bottom surface here? Z equals 0. The bottom one is the xy plane. And the top surface is this one. What's that? Well, again, you try and write it out here. It's you write z equals square root 1 minus x squared minus y squared, and square both sides. You got z squared, and sure enough, he's right. 1 minus x squared minus y squared. So it's equivalent to this, except this radical sign means z can't be negative. So it's equivalent to this with, together with the restriction z greater than or equal to 0. Add x squared plus y squared to both sides, and you see this is equivalently to x squared plus y squared plus z squared. Z coordinate's non-negative. It's a hemisphere, right? So it's the of unit radius equals 1. That sits over this thing. It looks like this. And so what you get really is a quarter of a sphere. That's the solid. A quarter of the sphere that's over this semicircle here and below this part of the hemisphere. Once you sketch it, now you can convert it to cylindrical coordinates, and you just have to think of what does the cylindrical coordinates require. It requires that I have to go that simple type of region that we showed. It has to go over a simple polar region, right? The projection has to be a simple polar region, and then it has to have a top surface and a bottom surface. So in cylindrical coordinates now, once I sketch it, I take this region of projection and I try and rewrite it as a simple polar region. Well, I can say, oh, it goes from theta equals 0, a beginning ray, turns around to theta equals pi between two rays, and then an inside radius and an outside radius. The outside radius is r equals 1 because it's a unit circle. The inside radius, we can take r equals 0 is the inside radius. And so we go inside radius to outside radius, beginning angle to end angle. And lucky us in cylindrical coordinates, it's constant endpoints, 0 to 1 and 0 to pi, right? So there's the region R put in cylindrical coordinates. And now I need the top surface and the bottom surface. So if I sketch these in cylindrical coordinates, the bottom we said is z equals 0. That stays the same because it's the same z coordinate. But the top is different, right? The top one, if I write x squared plus y squared plus z squared equals 1, I have to convert that to a cylindrical coordinate equation. Remember, x squared plus y squared is r squared. So this is actually r squared plus z squared equals 1 in cylindrical coordinates. You can also just put x equals r cosine theta, y equals r sine theta. That works. Then it reduces to this. It just takes more work. So use the quickest conversion you can. And now you have to write z as a function of r and theta for this. So you rewrite this as z equals plus or minus the square root 1 minus r squared. To get the top half, you use the plus. Right? So this was z greater than or equal to 0. This was z greater than or equal to 0. And this one you drop because the square root implies that. So there's the top surface equation converted to cylindrical coordinates. So now it's not too bad because now rewriting, if I call this star, I can also convert this integrand. So now the original integral, maybe I better rewrite it. Minus 1 to 1, 0 to square root 1 minus x squared, 0 to square root 1 minus x squared minus y squared, e to the minus square root x squared plus y squared plus z squared, dz, dy, dx. This is your integrand f of x, y, z. This can be rewritten as the triple integral over the solid G of e to the minus, if again we call x squared plus y squared r squared, it's e to the minus square root of r squared plus z squared in cylindrical coordinates. dv, and I'll put r theta phi, r theta z. To indicate I'm converting it to cylindrical coordinates. Now I put what the limits are from my sketch. Again, in this triple integral, maybe I should put these limits on here just for, this went from theta equals alpha to theta equals, oops. Let me put this in the reverse order. I'm gonna put dz d theta dr. The way we normally want to do this is dz dr d theta, I should say. Dz dr d theta is the usual order. If you put it in that order, then theta on the outside goes from the minimum angle to the maximum angle, formula 1. R goes from the minimum radius, R1 of theta, thinking of the simple polar projection region, to R2 of theta in the simple projection region, simple polar projection region. And Z goes from the bottom surface, Z1 of R theta, to the top surface, Z2 of R theta. So that's the complete formula. And so that's what I need here. I need the minimum angle. Well, theta from the projection goes from a constant 0 to a constant pi. The inside radius here is 0 and the outside radius is 1. In general, these can be functions of theta, but in this case, we picked a simple region, a really easy region. So it just goes from 0 to 1 constant endpoints. But in general, these can depend on theta, and these can depend on both r and theta. They're, again, partial integrals. And then this one goes from the bottom surface, which was z equals 0, to the top surface, finally a function of r and theta, it's square root 1 minus r squared. And then the dv becomes r dz dr d theta, because this is the infinitesimal volume element. Right, we just proved that it's not dz dr d theta, it's r dz dr d theta is the volume element. And then the integrand, e to the minus square root r squared plus z squared and so on. Here's what I need to do, that integral. Any questions on that? I need to raise the flag and star. I'll make sure that's reasonable. All right, now the nice thing is there's no theta dependence in here, right? This is a constant with respect to theta. I can pull the theta straight through. Also, this is integral from 0 to pi of d theta, right? Of this other integral. Now I can't pull the r clear through, but I could switch the order if I want. Right? What happens is if I try to integrate this with respect to z, it's pretty hard because e to the minus square root r squared minus z squared. How do I integrate that? That's actually a real difficult one. But if I change the order on the other one, write an integral from, oh, I'm sorry, I can't do that yet. Let's see. Actually, on this one, I think it says not to evaluate it. When I think of it. No, it says evaluate it. Okay. Something missing on here. Let's see. I did a slightly different problem than they have here, but, doesn't make any difference.
You want to do like the partial on this first time?
Yeah, you do the partial integral the first time, but it's still difficult. Thinking this isn't what the,
Maybe the question was asking to integrate in spherical coordinates because it'd be e to the negative phi.
yeah. It says cylindrical or spherical, but I thought this one was supposed to be cylindrical. I guess this was spherical is what they wanted. I think you're right on that. They wanted you to do it spherical, which I didn't write. I looked at it and it looked like it would come out in cylindrical, but I think you're right. Let's just leave it like that and say this is a converted integral. If I would have made a different top surface, this would have been a little different. So let's just say here's the integral in cylindrical coordinates then. Looks a little easier. It's actually still difficult. We might be able to do this because you can use that trig substitution. When you have a square root a squared plus z squared, you can substitute z equals a tangent, or tangent theta equals a tangent theta equals z, and get this thing to work, or in this case, r tangent theta equals z. We might get it to work that way, I don't know. But I think this is hard. This one should have been done in spherical. All right, so there's an integral converted to cylindrical coordinates. This is also slightly different. They put this to the 3/2 instead of the 1/2 in there, so I changed it a little bit. But that's what you do to convert these. Sometimes you get something that's real hard and rectangular, but you can convert it to cylindrical and make it a little easier. This one didn't quite go, but almost. All right, now we want to do the spherical coordinates. Now what you have is you need to get a region like this. You have to get theta going between two constants, theta equals alpha and theta equals beta. These are angles in the xy plane. Remember, theta turns in the xy plane. And then over that, you want phi to go between two constants. So this is a pretty restrictive kind of region, but it is the one that comes in practice. So over this, you put the restriction that phi goes between phi 0, let's say gamma, and phi equals delta. So theta and phi going between two fixed angles. And then you have a region where you can put it like this. Let's put, here's phi equals gamma and phi equals delta over this one. And then we'll put phi equals gamma and phi equals delta over this one. And we have a region that looks like this. It has an inside surface, rho given as a function rho 1 of theta and phi, and an outside surface, rho equals rho 2 of theta and phi, and phi and theta are restricted to go between two constants. And that's why you get these straight edges here. And this is your solid G. Has to look like that. If you make a solid like that, then you can integrate it in spherical coordinates. There are some others you can do, but this is the only kind that are useful in practice, and the only kind we're going to learn is if you have that kind of a solid G between two constants for theta and alpha, and two surfaces, functions of theta and phi on the inside and the outside. A similar derivation says, well, suppose I break this up into subsolids, each subsolid incrementing the three variables between constant values. So I have constant values of rho. Here's rho 0, rho 1, up to rho little n or something. And then I have incremented theta, and so I partition it in angles theta. Oh boy. Theta 0 to theta k or something. And then I partition phi in this direction, phi 0, phi 1 down to phi j or something. So I partition each of them up. Then I get little subsolids that look like this. Between two angles, phi equals phi k minus 1, and phi equals phi k, with an increment, delta phi k, their difference. Unfortunately, this one is so complicated, I'm going to have to do a little bit of hand waving. The details are just too much. But that's what happens. So the phi goes between two constants, and then you have an increment delta phi k. Then theta is kind of curved on this side, has an increment from angle theta equals theta k minus 1 down to angle theta equals theta k. And the increment in the angle here is delta theta k. And then the increment in rho is delta rho k. So here comes the hand waving part where I don't actually prove it. But this looks almost like a rectangular box, right? It's not a rectangular box, but it looks kind of like one. To within a close approximation, when you say that the volume of this, suppose this is the kth box, kth subsolid of a total of capital N subsolids. What is it? It's approximately equal to the approximate length times the approximate length, width times the approximate height, right? So I can take length times width times height approximately. Well, the length could be delta rho k. Right, that could be the length, approximately, right? I mean, actually, that one is exact because it's a straight line. But the other two are arcs of circles. And what you have is phi k comes off this circle that goes around like this. And so what's the arc length here along a circle? Remember the arc length along a circle, if you take a circle and you increment with an angle delta phi k and radius r, let's just call it phi. The arc length here is r times phi, right? S, the arc length is r times phi from geometry. All right, so that if you take 2 pi, you get 2 pi r, the circumference of the circle. It's the fraction of the circle subtended by phi. So this is the formula for arc length, is the radius times the angle subtended. Well, the angle subtended here is delta phi k. So that you have the radius out here is some intermediate value rho k star. I'm going to draw this in blue. Rho k star, the radius at some intermediate point, times delta phi k star is the approximate arc length along here. So we'll say that this is the approximate width, or if you will, this is the length. Whichever one we call length, height, and width. And this one here is a little trickier. This goes around in a big circle like this, and it's not radius rho k. It's not, the radius isn't rho k star, some intermediate radius, because what you have is the radius of the circle is up here on the z-axis. The radius is actually rho k star cosine bk star. If you take, right, you're thinking of taking a circle at a height z for theta, it's not like phi where it rotates around at a constant radius at rho. It rotates at this constant height z equals rho times cosine phi. And so this one is the approximate radius, rho k star, some radius in this k thing, times cosine phi, that's the radius, times the angle delta theta k. So once again, this is the radius of the circle here, but theta goes around, times the angle subtended, gives the arc length. So that's the approximate arc length along the edge here, is approximately rho k star cosine phi k star. We'll put a k star because it's a k piece and some intermediate point, times the angle delta theta k. So that's the approximate length along here. The approximate length along here is rho k star delta phi k because it's radius times angle. And then this one is not an angle, it's a straight edge, it's just rho k star. All right, so there's the approximate volume of the k piece. And it turns out the error from being a rectangular box goes to 0 as you take the limit of the number of pieces going to infinity. So now, the triple integral is evaluated as follows. You say triple integral of f of x, y, z dv can be the limit as n goes to infinity, the number of subsolids, of sum k equals 1 to n over the n subsolids, of f at an intermediate point, just like in cylindrical, xk star, yk star, zk star, any intermediate point. And it won't matter which point you pick as long as f is continuous. Now, dv gets replaced by delta vk. So this is the same thing we wrote for cylindrical. But now delta vk is different, or not delta vk, it's vk. Now vk is different, it's this. So it's limit n goes to infinity, sum k equals 1 to n. Xk star gets replaced by its equivalent spherical coordinates, rho, sine.
Sir, your camera's gone blurry.
Oh no, I wonder what happened. I didn't do anything to it.
Fix
Can't
itself.
tell here. Is it back? I can try moving it, maybe it'll do something.
Yeah, it's better now.
Okay, thank you. Tell me if it does it again. So you replace x with rho cosine theta sine phi, but it's at some intermediate points. You say rho k star cosine theta k star sine phi k star is some intermediate point x k star. Y is some intermediate point rho k star sine theta k star sine phi k star, and an intermediate point zk star is rho k star cosine phi k star. And then I have to multiply it by vk, which is this expression, times rho k star cosine phi k star delta theta k, I'll put it here, delta theta k, and then rho k star delta phi k delta rho k. So that's what it looks like. Here's your vk. Now what you do is you can multiply in any order, so you interchange these two. You put rho k star over here. Delta theta k here. And now what have you got? Put a triple integral, right? Limit of the sum of this integrand, delta theta, delta phi, delta rho. And so what you have here is a triple integral over this, where theta can be put on the outside, goes from alpha to beta. Phi can be put next, has to go from a constant gamma to a constant delta. But rho goes between two surfaces, rho 1 of theta phi and rho 2 of theta phi. And then the integrand is f with these when they get rid of the k stars, right? Because it's just the definition of triple integral. This is f of rho cosine theta sine phi, rho sine theta sine phi, rho cosine phi. And then the little volume element here is rho squared cosine phi. That's the integrand, right? The integrand includes a rho cosine phi, and then d rho, d phi, d theta. I'll put them in the other order here. D rho, d phi, d theta. I can multiply these in any order. And if I put them in this order, then I can put theta on the outside, then phi, and then rho. And the idea is write the inside integrals over rho, and then next over phi, and next over theta. And here is how you evaluate these in spherical coordinates. So we can say the triple integral of a function, a continuous function, f of x, y, z, dv, can be evaluated this way using spherical coordinates. And admittedly, we have to leave out a lot of the details on that one. But that's just to show you where the rho squared cosine phi comes from. It comes from the fact that it's delta rho long, rho delta phi length, and rho cosine phi delta theta long, or height or whatever, and the three of them multiplied together give you the little volume element. You say this is approximately a rectangular box. You can look at the book and see that also, it'll do it in more detail. But now you see you can only do it over this kind of solid where rho and theta go between constants. I'm sorry, phi and theta go between constants, and rho goes between two surfaces, functions of theta and phi. So you have an inside surface and an outside surface. Rho equals rho 1 of theta and phi is the inside surface. Now rho equals this function is the outside surface. And here's the kind of problem that this is screaming to evaluate. Suppose I wanted to find the volume of the ice cream cone, right? Every college student wants an ice cream cone, I hope. find the volume of the solid G given with an outside surface x squared plus y squared plus z squared equals 4, and a bounding surface z equals square root x squared plus y squared. Why would I want to do that in spherical coordinates? Well, you don't want to do it in rectangular because these are terrible, right? If you write z as a function of x and y and put that in the inside integral, you've got a terrible integral you probably can't do, all right? So we want to convert it to spherical to make it easier. But when you sketch the region, then you see why. First volume is the triple integral of 1, right? So the integrand this time is just 1 dv. All I have to worry about is the integration limits. What are they? You sketch the solid and see which coordinate system you want to use. This one is what? Yeah, in 3 dimensions of a sphere of radius 2, right? X squared plus y squared plus z squared equals r squared is a sphere of radius r. The square root of this at the origin. Sphere radius equals 2. What's this one? If you square both sides, you might see it. Z squared equals x squared plus y squared is a cone, right? Except z is the positive square root. We also non-negative square root. So z has to be greater than or equal to 0. It's the half cone. Oh, a half cone is perfect. That's phi equal to constant, right? So when you have a sphere that's rho equal to constant, a half cone that's phi equal to constant, that's perfect for spherical coordinates, right? So we'll draw the sketch, and z equals x squared plus y squared. Z squared equals x squared plus y squared is this cone like this. Suppose you rewrite that in spherical coordinates. This is also z equals r, which you can write it as z equals rho sine phi. That's not what I want. Sorry. If z equals r, that means that this is actually a pi over 4 angle. And so this is phi equals pi over 4 is its equation. Right? If z and r are equal, then this is a isosceles right triangle. It's a 45, 45, 90. Z equals 4. Z equals pi over 4. Is it? That's the half cone here. And then on top we have the ice cream. That's r equals 2. The sphere of radius 2. So what we have is a region of just the type we just described with, well, what does theta go between? Theta goes all the way around. And so what we have here is to sketch this solid G. Is phi goes from straight up 0 down to pi over 4 to stay inside the cone. 0 less than or equal to phi less than or equal to pi over 4. Rho goes from 0 at the origin out to 2 to stay inside the sphere. These are easy. Take a little visualization to get used to. But theta is arbitrary. You can go all the way around from 0 to 2 pi to sweep out the solid once. Right, so you can let phi go from 0 down to here, and then for each of those, you can go arbitrary out, and you go all the way around, and then bounded by this sphere on top. So that's how the solid G works. They actually all go between two constant endpoints to sweep it over the cone. So I'm going to say this is the integral, and you want to always, on these spherical coordinates, put theta on the outside, then phi, then rho. And so theta goes from 0 to 2 pi. Phi goes from 0 to pi over 4. This is by double star, I guess we should call it. So minimum theta to maximum theta, two constants. Minimum phi to maximum phi, two constants. And then inside surface, the inside surface is this point, rho equals 0. And the outside surface is the sphere, rho equals 2. And then the integrand is 1. But we've got the volume element, sometimes we call this dv, in rho theta phi coordinates, is rho squared sine messing this up. Let's see. I wrote that backwards. This should be rho. When I wrote this derivation, this should have been sine phi k star. Oh, why I got off on cosine? That's sine phi k star and sine phi. Oh, I messed up your major formula here. Sine phi k star and sine phi. Sorry about that. Rho squared sine phi d rho d phi d theta is the little volume element. There it is. So by double star, and I don't know why I wrote cosine now.
You said when you did the second one, weren't you the second one? Oh, it was at the very end.
Yeah, so sine phi here and sine phi k star here.
Okay.
I just wrote the wrong arc length around there for some reason. Okay. So here's what I have to evaluate. But now look, since these are constant endpoints, I can take this partial integral. I can take the sine phi out and put it into here, right? It slides out, and then the integral over rho. In other words, I can slide these apart because they're. I can pull constants out and write this as integral from 0 to 2 pi of d theta, integral from 0 to pi over 4 of sine phi d phi, which I pull out of this integral because it's constant with respect to rho. Integral from 0 to 2, rho squared d rho, and so it decouples like that into the product of three integrals. And now this one, this is just theta evaluated at 2 pi and they're going to take the difference is 2 pi. Integral of sine phi is minus cosine phi. Plug in 0 and pi over 4 and take the difference. And then this one is rho cubed over 3. Plug in 0 and 2 and take the difference. So I wind up with 2 pi times, let's see, cosine phi of pi over 4 is square root 2 over 2. So I get minus square root 2 over 2. And then minus, at 0, cosine is 1, so it's minus a minus 1. And then this one is just 8/3. So let's see, the volume of the ice cream cone is 16 pi over 3 times 1 minus square root 2 over 2. There we go. All right, so there's an example in cylindrical coordinates, an example in spherical coordinates. What I'd like you to do for homework is try 9 through 19 odd. It's 14.6 the next time. 14.6. 9 to 19 odd. That'll give you a good smattering of problems. Some of those you may just want to set up and make sure you get it set up right. And some of them are just to do that, and some of them they want you to evaluate the whole thing like this. All right, see if you wanna do any more of these next time, otherwise we might move on to surface integral probably next time, which is probably the hardest topic. But then I think things will get a little easier for a while.